because these are pretty good questions. So I just covered this point here where I said that the risk that they speak of is only the additional added risk of sampling. All right, let me kind of make that point clear, because I think this is sometimes not understood very well. And I'm going to look at this paper that I wrote a while back called the Brawl method, because in this I detailed out how do I get rid of this here? Okay, how my simulator worked, and so because I wanted to understand this. So first thing I discovered was that margin of victory, and this is congressional contest, which is not really a good sample perhaps, because it's congressional seats, which are highly gerrymandered a lot of times. But the most typical margin is about 25% between the winner and loser. Most of everything above 10% here is like 90% of the contests are, I have another chart that maybe I put it down here, I don't see it. Anyway, that did it the other way, where you see what is the percentage greater than a certain number. And it's really these down here, isn't it, that we're interested in. You know, the rest of these, you know, once you get above 20%, the likelihood of somebody being able to hack it that hard. Of course, these are unopposed candidates down here, and sometimes they're not, well, pretty often. But these are the ones we're interested in that are close. And it's luckily not typical that they're close. Typical is they're a little bit further. But Paul did a little bit better analysis of this, where he took not these congressional seats, but every kind of a contest. And it is, they're not as strongly skewed toward that way. But in any case, let's move on. I won't go into the exact model, but here is where we're doing a ballot comparison audit. Okay, now in ballot comparison audit, what you're doing is you're comparing a ballot to the cast vote record for that ballot to see if they line up. And if they line up for that contest, then the difference is 0. All right. If the cast vote record says that the winning candidate won by more than the ballot says, so basically the cast vote record was lying or wrong in such that the stated winner was overstated. They call those overstatements. So these are the cumulative overstatements as you go. So you go up to 500 ballots here in comparison, and we're looking at maybe 20 to 30 overstatements. That's what we're looking for if this election is hacked. So in this election, in this simulation, I have 100,000 ballots, you know, in the election. This is a number to use. And we've got a margin of 3%. So that means that, like, after 2,000 ballots, you're going to be up here at around 60 ballots that have overstatements. But notice that these audits, they sometimes hit more overstatements right away, and they sometimes don't. But they're going to be clustered around this line that goes up like this, because this is the rate that you're expecting ballots to be different in order to accomplish that 3%. So if what is 3% out of 100,000, 30,000 would be 10%. So 3% is 3,000. We got to find 3,000 ballots in that 100,000. The 3% difference means that we're looking for just a barely, like it used to be tied up, but except for one vote the other way, and the result was 3%. Now, in reality, the real result, the actual ballots would probably not be exactly tied up by just one vote, but be more like the other way by 3%. So you'd be able to detect a 3% a little bit easier than this. But we're assuming that 3% margin, and you would be detecting it at this rate. And these are a few. Now, if we add more, you add 1,000 trials of sampling the same election. This is the same election, same 3%, but we have different audits, and they're going to, by chance, you're going to go up and down as to how this collects. But notice that it's all clustered around the central line here, which is the rate where you expect this thing to go if we go all the way to the end. And also, I'm going to add in here some noise. I don't know if I added it here, but we have what the overstatements. This means overstatement by 1. Okay, that means that on a given ballot, you may have a change by just 1 vote. So either the vote for the candidate that was stated in the outcome was not there, and it was just empty, it was blank, or it was an overvote, and it was credited to the one guy who won, but in reality it shouldn't have been. Or it was for the other candidate, it was actually said to be an overvote, but is actually a vote for the other candidate. That would be a change by just 1 vote. But you could have a change by 2, which would mean you erase 1 and add the other one. And so we're assuming that you're not going to have overstatements by 2. There's only 1 vote or under overstatements, and that means you're going to need more ballots to do this. But that's more common. If you ever found something where you had both a candidate added and subtracted, this just doesn't happen in a machine. So that's not going to happen. So this is where you see there's a distribution here of this thing going up at this rate. That's for the hacked election. Now moving on down, we're going to add a unhacked election. Now this has a distribution here because we're adding some noise. 0.2% noise, meaning that there was some misinterpretation of the marks, but the election was not hacked. It still comes out to be for the candidate. So all of these errors offset each other. You had errors in both directions that they offset. So that's the noise. And I call that noise because it doesn't affect the output. But we have this one. If you didn't have any noise, you'd have a line just set here on 0 with no deviation at all, because there would be never a difference because the election is not hacked. All right, so those are the 2 distributions that we need to tell apart. And then this one here, I just draw some lines around it, showing that, I don't know if you can see this, but I'll zoom in a little bit. Oops. So you see here is the average, and this is not a line that's drawn as a line. Instead, it is the average of all of the samples at that point, averaged out over 1,000 different samples, and it's right dead on. So it does waver a little bit, you can see, because it's not exact. But this is along a line. If you cut it vertically like this at any particular count, you could be up this way or it could be down that way. So you can see here, we go up 20% in this region. In this area, 80% of the votes are in here. And up and down, that's 20% left. And here's 90% are in this 10% to 10%. And there's only 10% out there, and so forth until you get down here to 0.1%. And indeed, out of 1,000, we see one audit that seemed to exceed that. Now, this is not actually, these lines are not determined by the actual samples in this case. They're smooth based on how far away from based on normal curve. All right. Okay, so this is the hacked one, and then down here, I guess, let's see. So let me make this smaller. So essentially, this is the distribution of the red case is determined by the normal randomness in the samples, and less so by the noise. It's mostly the sampling that you're doing around whether you pick up those deviations or not. And down here, this is all based on the noise, and you have the same numbers down here. And then this line will go up. It'll tilt up if you have a larger margin, and it tilts down and gets closer to this thing. And then you can see that these things where they cross, that's what we're interested in. So as they come down here like a pair of scissors, this thing sort of squirts out to the side pretty fast. And as you come down and your margin gets closer and closer, then it's going to squirt out really fast as the hacked election is closer and closer to the unhacked one. But what we're interested in is where we can determine, what we want to determine is, are we the green or are we the pink? That's what we're trying to focus in on. This is how I look at it, because I like things that are concrete and not so much, I'm a math person, but the equations they have are just berserko, I think. So anyway, this brown line is the equal risk for both distributions, and it crosses where the distribution curves cross. So here is where the 0.1% and the 0.1%, they cross right there, and that's going to cross there and so forth. So if you wanted to have a 0.01% risk of not making the mistake, you would get 614 samples in this case, and you would expect 5 overstatements. You would allow 5 overstatements, because those 5 overstatements would be up to this line here, 5, and that you'd say, well, I'm still in the green, but if I'm more than this line, I'm pretty sure that I'm pink and not green. And then you'd say something's wrong. And so this is the way I would do it. This is, I think, a really understandable way to do it, to say this distribution up here, this is all having to do with where you happen to go based on sampling, and that's it. And this is what the risk limit they're talking about is where you need to, where you want to, how much risk do you want to take here? Now, if you want to take a 5% risk, then you would go down on this line. I think it's the one. Anyway, it's down in here somewhere. And I think I zoom into that more. Let's go down. Okay, this is a comparison of different methods. I took the Stark method with various thresholds based on p-vals and risk, and this thing that he calls alpha, okay, which he just dreamed up from nowhere. But these lines here, and you can see that in actual runs, the S4 RLA is Stark's method, and it's called the super simple simultaneous something risk limiting audit. And so it's at 4 S's in a row. These mathematicians like to come up with cute names. So these yellow dots are when he correctly identified the green, and the black ones are when it incorrectly confirmed and said this was the green audit. All the way up in here, he was saying it's green. So I was thinking, God, that seems wrong. Why would you, when you're this far out, why would you still say that's green? It doesn't make any sense to me. But it's the way he set it up. And these lines here, I tried to figure out what would happen. And so I drew these lines based on when these black dots would show up based on different levels. And it's way up here in the pink. So you get a lot, it's a really lenient audit. You get a lot of identification of a hacked election is fine. It's fine. Okay, here is the gamma. Oh yeah, I called it gamma, I'm sorry. It's various gammas and where the thresholds were. And I analyzed that based on where these thresholds would be. Again, it's way up here. And these should be down here where this brown line is, in my opinion. Here's different, a single gamma and different lambdas, another variable that he has in there. And he moves this up and down here with lambda, but really it doesn't make a lot of sense as to what he's doing when I think just the brown line is where it should be. I don't know what he's trying to gain from this lambda thing. Certainly gamma doesn't do really any good. It just moves us up way up here where it's not supposed to be anyway, way up here, and never gets, anyway, it doesn't, all of it is a mistake in my view. So then we have this other, a statistical, these were Bayesian audits by Ron Rivest, and I tried to run his program, and I just got nothing. I communicated with him privately, and I says, look, you're not getting, this is not working. And it could have been that I did not know how to do it, but basically it just was all over the place. And so then I said, look, let's use a different method here. I'm going to call it Brawl. And since they love making up names, I call it the Balanced Risk Audit with Workload Limitation. You know, you have to come up with something. So Brawl. And so my point is here is that we've got a couple of points on these charts that we can identify. And the first one is where the we're basically we're down here and we're saying we expect there to be 0 overstatements in the green audit if we're green, but if we're pink, it's very unlikely that we're going to be down here because this is the 0.01. Only one time out of 1,000 we would be this far away from that line. So that would be the first step, is getting that point, saying I'm pretty darn sure if I am at 0 overstatements, then I'm good. But if you had some overstatements, you'd have to wait until this point, until you had at least you're coming with you're outside, you know that you're not green, and you could say, now I'm pretty sure that I'm pink, and so I'm gonna say stop. This one, if you're 0, you can say I'm good, I can stop right here. But if you're up in this area, you're not sure enough yet, you have to wait for this curve to get out of the way, and so you would go up there. So in essence, you would start here and you would do, in this case, 3.82, 362 minimum samples for this case of a 3% margin. Still seems like a lot to me. Pulling 362 individual ballots out. And then you would do 643 samples out. And that also, if you wanted to do a 20% conservatism, which I think is not a bad idea, you just move this out by this amount, and you go to 435 and 782. Now you're saying I'm 99.9% certain that I am not hacked and that this is the result. Why would you want to stop at 95% if you can just count a few more and go to these places? And given that the way that Stark's method would go way out there anyway, and his just didn't calculate it right. At this point, you can see that the samples for the pink one, which is hacked, versus green, you know that they're different. And so you don't, this is if we had 3% margin and 0.1% risk, 99.9% sure, and an additional 20% conservatism. You would know for sure that these are separated, and that would be the goal of the process. Now, the second part of Brawl is this, workload limitation, because we know that as the margin gets narrow, the number goes up exponentially and at 1 over X relation. And you can see them here. So this is the margin, and let me see if I can kind of explain this. This is the percentage margin down here, and this is how many samples you need. And this is for brawl. Okay, so essentially, if you did it my way, and you had those picking those points that I showed you, then you can see here that there's different scenarios where you decide, but in all cases, they're nice and constrained down here at 10% margin, no problem. But as you get down into close election, and guess what? It goes up through the roof. You start to need thousands and thousands of samples. So then at that point, I was saying, look, we're going to limit our workload here. And once we start to get up, we're going to move from the green line. Like, we will start here at this green line and be very conservative and want to make sure that our sampling is good when we have a large margin. But then when we start to go through the roof, we move down and we become less conservative, and we allow more, we limit the workload, but we're still gonna be, you know, sampling to a certain extent. It's just that the number of samples, like the number of samples here, are not too different if you're very conservative or not conservative. But down here, it starts to be huge, because if you look down here and you say, I'm not going to be too conservative, but I'm still going to be reasonable, you're 1,500 samples, whereas the other case is like, it's not even on the chart. So that's the idea of workload limitation. You have to do something, okay? Either you're just going to stop and say, okay, I'm going to count everything, but really you don't have to do that. You can say, well, I'm just going to be less conservative. Instead of 99.9, I'm going to go down to 95 or 90% and be a little bit less conservative, but still, that's what brawl does. And then when you are being less conservative, then you have a little bit of overlap here. You might make mistakes between the two. And then I was in favor of having a chart like this, where you just have a margin and there's no math involved. You just have the number of samples and what the maximum overstatements can be at that point for that margin. So most of the time, you see, like in terms of the number of samples, say here at 10%, it's 85. It goes up to 3,300 when you get down to half of a percent. And there's a big difference between 0.6 and 0.5. You're adding nearly 1,000 more samples. It's going way up. Okay, now I'll jump into the polling audit. This is a little bit of a confusing diagram, but I've showed this one before, but with less junk on it. You have the green election is the one as stated at 10%. So it averages out to this point. And we're only having 4,000 ballot samples here out of the 100,000. And when you first get your first sample, right, you get first ballot out and it says, okay, vote for candidate A. You're going to be at 100% A and 0% B. You're going to be up at 100. This is 40%. So you're going to be way up at 100 past the thing on the first sample. Then the next sample, you know, let's say it's a vote for B, you know, so you'd be down here then, but then the average, you'd be right at the middle, 0 so far. And then as you go, so there's a whole bunch of moving around here as you first few samples, but then it starts to go toward the average, right? And so law of large numbers, it tends toward this average. And if you go way, way out, then it would come down to, you know, not much variation for a very long time, because that average is set. If it's not very long, as we saw before a couple of weeks ago, if you have a fixed number and you don't do resampling, you don't put the sample back in, then the curves still have quite a bit of variation, even up to the very, very end. But they will converge at that end. Anyway, this green curve then is the unhacked true election, and with no hacks. And this is what if you were sampling this election, this is how it would look. Now, this is like a law of nature. This has nothing to do with any methodology or anything else for calculating what the risk is or anything. This is just at a certain point, what is the margin that you've collected so far amongst all your samples. You collect a sample, you look at it, you assume you're getting everything. It's like you're asking voters their opinion, and you're going to have this opinion poll that's up at this point, and the dispersion of this is going to be this margin of error that you hear about. Like, what's the margin of error? So this is going to get narrower and narrower as you go out. At 2,000 samples, you can see these two distributions are starting to separate. And that's usually where you need, if you're going to do an opinion poll, you got to get at least 1,000 or 2,000 samples, no matter what, because in order to get these apart enough. So at a 10%, you can see you'd have to get, this is the risk now. So at 20% risk, this is the simulation method that let me look into that some more. So this is the simulation analysis, which is the way I would do it. And you see here at 20%, what is that? That's when the green distribution has these blue lines. And this one right here is a 20% out from the average. And there's the other one right there, which is 20% over. So 80% of all of the trials are in this spot, and there's only 20% above there and down there. And then the next one is this line. When this line crosses that one, is right there. And that's where you've got a 10%. Okay, and then this one is the 5, and so forth. So when you draw these lines, I say, here's how many samples you need. You need 262 samples, and 583, you need 1,000, 1,400, and this is the average sample number as advertised by some of the other methods, and they actually are at first over what we do, but they're very much more aggressive here of doing it. And these different colors, kind of hard to explain, but these are trials of different methodologies, and where they either stopped or said that everything was okay. So we have the CLIP and Bravo methods. Bravo is the one you probably hear about the most, and so that's this orange, and they actually wait until a certain point. They say, we're not going to do anything until after a certain point. And these are the points when they say we're going to wait. And then here at 20%, they call it off for these. They say these are all green, and then down in here is where they actually make a mistake, and they say this is green, but it's all these blue dots are incorrect. When they've actually made a mistake here and said, okay, I'm good, but and actually it was a hacked election. So I was evaluating the Brawl method and these other methods to see if they would be better, and indeed we would also, well, we would wait, and if you're above, like, if here's the midpoint here, and you could say, well, if I'm above this, and I'll show you, because in the next picture I have kind of the proposal. So the proposal is that you, if you wait to a certain point after you get a certain minimum, and if you're up in here, like you're very much outside of the pink, then you confirm all this and doing blocks of 500, confirm these, and then you continue to audit in here, but also you fail early on these. They never have early failure in the other methods. They just continue to pull samples without any indication that they should fail early. So that's the addition that I would suggest. So then here we have the number of samples in Brawl for different margins. Here's the margin of like 4%. You need a lot. So if you had a risk limit of 5%, you'd need, around 7,000 samples. So you're pulling the samples and you're adding up the margin of victory in your sample versus the stated margin of victory. You're not comparing ballot to ballot. And then I talked about batch comparison, but I didn't do it very rigorously at this point, but I'm in favor of batch comparison audits. And I did it more later after I wrote this paper. I was also trying to find out like what the processing costs would be, because if you do a ballot comparison audit, you have to pull individual ballots. It's a lot of work. Polling risk limiting audit, you've got a lot more ballots that you're going to be pulling, and they're individually pulled. And then a comparison risk limiting audit, and then image validation, but I'm a little bit, I'll talk to you about that in a second. And then combining the strategy. So that was a paper that I wrote a while back, and trying to get myself understanding this so you can see what I went through. And that was around 2018. Okay, so questions about this? Oh, I see you have your hand up, Paul. Go ahead.
Couple of questions. Let's say it's an extraordinarily close race. You got, 100,000 voters ballots, and the margin is 5. That's within the noise.
Yeah.
And so do you just say, I'm sorry, there's no way we can determine this?
No, they would have to do they do a manual recount as best they can, and they go with that. But I watched them do these manual recounts, and typically what they're doing is they're comparing with the computer result.
Yeah.
And so then it's not the same as an error rate of just people sitting in a room and trying to tally, because you're comparing with the computer. So you can say, well, and usually what it is like, we didn't get the computer results, so we must be wrong in our count. So go back and try it again. And then they try it again. And sometimes I've watched them here in San Diego do it, maybe half a dozen different times with different teams, trying to get at least the same number out of it.
Okay.
Yeah.
The second question is, if you have a rogue machine somewhere, which is introducing massive errors. It's not a hack, it's just, a bad machine.
Okay.
How would you ever know that if your sample is drawn more or less uniformly?
Well, if you had it clustered in one area, you would hit that. If you're randomly sampling, that's a good thing about random sampling, is that it will hit it. Like in this simulation that I do here, I actually do it that way because it doesn't matter where the samples are. I actually have the entire range of ballots, and I say that these first ones are modified, and these are modified by one overstatement, one understatement, and so forth. I have all the modifications all in one spot. Doesn't matter where they are, because then you're randomly hitting it. Now, if you took those and you also randomly distributed them, by randomly doing it, you'd have the same rate of hitting them as you would if they were grouped. So if you have full random distribution, random sampling, you do it right, that's the best way to catch anything. Now, the thing is that with batch comparison, this is even harder, because you're assuming that you have a person who is a malicious actor who is trying to hide his changes. And so it becomes what they call the inspection game, where you have an inspector and a fraudster, and the fraudster is trying to outwit the inspector is trying to outwit the fraudster. And in that case, the best approach is also random for both the parties. But then it gets complicated because the batches are not all the same size. So then the question is, should you choose a really big one and modify that? Or should you choose a lot of smaller ones and modify those, but you get less out, bang for your buck down there. But you have to modify more than that. and so then it turns into be a weighted, it's best to do weighted by the number of ballots basically in the set is good enough to do it. But you should use weighted sample. But anyway, yeah, so so yeah, your question is, what if it's just one batch? Now, this is an important question though with regard to image audits, because the assumption there is that there might be a hacked machine to modify the images before they turn into a cast vote record. So in that scenario, you have a fraudster, right, who has hacked the machine such that it takes a picture of the image, but then the image itself is modified so that either they move the bubbles around, or an easier way to do it would just be get rid of that image and put a new one in, which you know what the numbers are. So like, let's say you'd be accepting ballots, you accept ballots, and you know, okay, these are the ones for candidate A that I want to win. I'm going to keep that one in memory. Then this person votes for candidate B. You say, yeah, I got it for candidate B. But then when you took the image, you say, get rid of that one, put in the one I know is for candidate, the other candidate. And I tally up the cast vote record on this one. So now the image and the cast vote record match. So Ballot Image Audit won't see it. The paper is different. So if you look at the paper, you would find it. But the point I'm making is that this is aligned with the scanner. So you would really optimally want it to have an audit that would at least cover all of the scanners to some extent, or at least it'd be best if you got some samples from all of the scanners to see. Instead of just choosing one scan, you want to make sure that you're covering those scanners, and maybe not taking as many samples as you would otherwise. Because I think it's, as we were looking at this set of hazards earlier on, we have all of the hazards kind of modeled in this diagram. And these are the election hazards that we went over early in the meeting. A lot of these you can't detect with any kind of inspection of the ballots, because at this point you get to the secure ballot. These are the paper ballots that you would be inspecting with an RLA. And this is the cast vote record that you're inspecting here, but there's all this other stuff up here that could happen that is never checked by this little bit of checking here. All you're doing with these is you're checking that the ballots are consistent with the cast vote record. Same with the ballot image audit, except we're getting the ballot images here, and we're testing the ballot images to the cast vote record. In both cases, like if you went back and says, well, I'm really worried about the images being hacked, let's check with the paper. You can do that, but you're still going to miss all the other stuff. So I think it's a little bit of a overreaction to say, well, that's the only thing that's wrong with the difference between, we're going to center on this one difference between ballot image audits and RLAs when they're looking at the paper, when they're also missing all this other stuff. And at least I'm being honest about it and saying, look, all of these things exist, and the risk is not what the risk limit that you're talking about is not the entire risk that the election would be changed. And I did actually publish an article about this called Comprehensive Risk Estimation, where I was trying to say, like, what are these other risks, and how would you calculate it? At least an idea of how would you calculate all of these risks, and then what would the total risk be? And it is different from what they calculate, for sure.
Good luck on that one.
Yeah. Well, at least we wanted, it was modeled after the equation used by what was his name? Anyway, he did the equation of artificial intelligence extraterrestrial intelligence. What is the likelihood? And you multiply all of the number of stars, potential planets, possibility that you had intelligent life on each one. So there's all these terms. What was it called? It starts with a Q. And I can't think of his name now, but it was the along that line of multiplying the terms together to find out what you multiply the confidence together. So you have 95% confidence that your election, these paper ballots match this cast vote record, but you only did one contest and there were 10. Now you're down to 9.5% certainty that none of the other contests have been hacked. So, by just centering in on this risk limiting audit thing and saying the risk limit is 5%, they're actually kind of lying to everyone to make them think that the election is a lot more secure than it is. Even though that doesn't hurt to do that. And it's very, very good because it actually, like in terms of saying how many samples should we have, you'd still want to know this, like how many samples would you need? If you are going to try to match up the ballot paper with the cast vote record, how many samples do you need? And then you can kind of ground those laws in mathematical sense. But as I said, as you saw, the methodologies that they use, like Stark's super simple simultaneous another S, RLA, actually makes a lot of mistakes. It's not a very good method, and at least in my opinion. But it's an equation it's just an equation that's sort of tight and easy to see, but nobody understands. And they say, yeah, I go along with what he says because of the equation. I don't really understand what, especially that one term, gamma, which he just threw in there from nowhere. The gamma makes no sense at all from any kind of basis of, like what I showed, at least in my little paper here, was I can show you graphically where we should draw this line and to separate the hacked from the unhacked, and where we would want to have a stepwise progression of first taking this number and then taking that number as a second step if you have any overstatements. But if you have a nice clean election and the green here is not, just this is the noise. If you don't have a lot of noise, you can have a nice clean election and you get right here and you have no overstatements, you could just call it off. So none of this, you haven't seen any of these other papers from all of these other workers that actually shows it in graphical sense where this is. Now, one thing that's cool is if you have a risk limiting audit, I can come in there, draw this. This is a reality of how you would sample it in both cases. And we can pull and we can put our little crosshairs with a circle and show where it is. So if you had say taken 500 samples and you had say 10 overstatements detected, you'd be right here. We could draw little crosshairs and we say, you know what, you're very likely pink and not green. So we want to go to a full hand count. Why wait? If you're way out here, you're not green. Why continue? But again, most of the procedures by risk limiting audit writers don't have a systematic methodology for stopping the sampling and turning to a full hand count. Okay, so I see, I want to thank Mimi, thank you for coming, and also Duncan Buell, two people I highly admire are joining us. Was there anything on your minds that you wanted to share since you're here, or we'll just continue with the other questions? Anyway, put your hand up if you have something. And let me go back to the questions just to make sure that we cover these. So now the issue is that you were mentioning this, and this is a really good question, Paul. You're asking exactly the right questions. What about all of the other contests? Would you need like 3,000 different sampling plans? And of course, if you have a tight, one tight county election, it's going to dominate. And you're pulling samples, then likely, if you have another county-wide election, it will get enough samples for that one too. So it's just simply the number of samples It doesn't really matter what the deviation is too much. If you get that number, you can determine whether you're, pink or green, if you will, on my chart. But if you have smaller districts, and as Paul was mentioning, all school districts don't overlap, and all mayor races don't overlap. All hospital districts don't overlap, but they may overlap with each other. So you have these districts like school districts, and those are going to be, weird districts compared to the congressional districts and the other ones. And they may be split and other things like this. So they may be hard to actually get enough samples for. And the good example was this one in Long Beach, which was 16 ballots out of the 100,000. Okay. A risk limiting audit will do nothing for you. You cannot take enough samples to find the 16. You're going to have to look at them all. Also, LA now uses voting centers so that those ballots are distributed all over the place. And you're not going to be able to get those precincts that you need. And so it used to be $25,000, and they instead wanted to charge them $250,000, 10 times more, to do a recount. And they said, you can go in and look at the ballot images on our computers one by one. You could see them, the ballot images. Of course, you wouldn't see the paper, but getting to the paper is just, it's also difficult, even though it's better to get to the paper, sure. But as a independent operator here of trying to, from a citizen standpoint, review these elections and make sure that they're right, they won't let us get to the paper. They're going to look at the paper themselves, and they'll always say everything's fine. But for us to get to the paper, we can't do it very easily. So we have to do one step up, which is ballot images. And yeah, we'd love the paper to be checked. One way to do it is like the guys in Wisconsin, they hand scanned certain precincts. They scanned them themselves on a different scanner, and they provided the images for AuditEngine to run on. If you decide to just do an RLA for federal or statewide races, this is the question, what about the other contests? And what they do is, in Colorado, they call this opportunistic auditing, in the parlance of RLA people. Opportunistic, so that means that we don't really intend to do those other contests, but we had the opportunity to do them because we had some samples that were included on there. And I didn't really understand that at first until I started to realize that they weren't intending to do all the contests. They were only going to do the main contest, and then just if there's opportunity, they'd do the other ones. So, but if there were some samples from them, then they could calculate the risk. And if there were enough samples to meet the risk, everything is fine. They say that one's validated as well. But if they didn't have enough samples, they wouldn't do anything. They wouldn't go and get more samples for those other opportunistic ones. So they don't do that. And so basically, they just stop. And actually, I don't even think that they calculate the risk, because why do so? Why calculate the risk if you're not going to do anything with it? If you calculate the risk and you see there's enough samples, then you pat yourself on the back. But if you don't, then you don't do anything anyway. So then having the risk limit doesn't do anything other than make it look like you're doing something. So in essence, in Colorado, they don't calculate the risk. So they just do the main contest. They calculate those and then blow off the rest. Well, we could do it. We could take their samples. They do collect the data. They just don't calculate the risk. In Colorado, when the margin did get really tight, they just did a ballot image audit instead. And they said, we're not going to do a risk limit. We're not going to do a full hand count. Just check it. And this is something that I want to emphasize here. Let's say that a ballot image audit does find something. You don't have to go back and check the paper then. You found it. You found something. You can check the paper if you want, just to make sure that your find was not incorrect. But if you find an error, usually it's going to be something else. Like, okay, there was a batch that was missed, not included. If you find a batch that was not included in a ballot image audit, you found something wrong. And you don't have to look at the paper to find out if it's wrong. So you only have to do the paper part if you want to say everything was fine. All right, now RLAs don't do all the contests, but ballot image audits do. So ballot image audits do all the contests, but they just don't look at the paper. And let's see here. I guess as far up as I can go. Then I mentioned down here that in Maricopa County, they had 10,341 ballots, batches of ballots. And I was recommending to them that they do about 300, or we actually increased it to a 1,000 batches instead of doing 10,000 batches. That would have been made their job at either 2.9% of about 3% of what they did do, or about 10% of what they did do. And that's
Mimi has her hand up. I'm sorry to interrupt, but she
oh
had
yeah. Hi Mimi, before I go on. Go ahead.
Yeah, hi Ray, thank you. Wow, I'm gonna have to hop off too. This is really interesting and I'm not grasping all of it and I missed a lot of it. So I'm sorry for that. But I just asked the question to everyone from hearing you, is this why it's easiest to steal small jurisdictions like state house races, school board races, and county supervisors? That's question number one. And then concern number one. Second, is anything that we propose ballot images as a solution for that can be circumvented or undermined by some kind of difference created between the paper ballot that the voter verified and the ballot images that are being relied on for these statistical audits? I'm still very concerned about that. I think we always have to go to the paper source, and I would love to see a big poster of that so I can look at your concerns elsewhere. But I still think the fundamental concern is between the voter verified piece of paper.
Well, that's true, but that is hardly the worst part of this. The difference between where the ballot images could be potentially changed as the ballot image is created, and then and we're down here if you see that.
Yep.
So inside the scanner, either here in central count, the ballot image is created and it differs from the cast vote record. So this is the one hazard that you're talking about. Whereas all of the things have all these other hazards. The registration, the polling location, voter validation, issuing ballot, and the marking errors, etc. All of these other things still exist, and they're different. They're different scans.
Yes,
every single one.
I do. I know those exist.
Yeah,
my
so
only point, Ray, I'm really focused on, because ballot images and their preservation, that is being argued presently with such a vociferous force by me and John Brakey and so many people, that the situation we don't want to get into is something I foresee because of the way the Republicans behaved 2 years ago when a federal bill almost, the John Lewis and the other Vote for America, whatever that was called, act. The Republicans started to go, okay, ballot images, but then never touch the paper ballots again. We'll just go with these images. That's going to tell us everything. We'll never see the paper again. I got suspicious because of that, because I'm a suspicious person after everything that's happened in elections since 2000. And therefore, I don't want to see a lot of work going into saying we're going to do this whole thing with the digital pieces, and we're never going to go to the voter verified paper ballot. Of course, I know those election hazards exist, and everybody is trying to be vigilant and change that stuff. But the piece we can't change is the digitization of the voter verified paper ballot. And so when I argue for ballot images, I'm trying to be very careful to say that my audit suggestion is you need to do a statistical comparison. You just need to, because that's where the voter verified their choices.
Well,
So
yeah, and no, I don't think that
Okay.
that anyone is denying that it's best to go after to look at the paper, but we need to have, and I show here, this is a paper that we started, which is a risk limiting image audit. So you would, the image audit does all contests and very fine-tooth review of the election, including all voter intent mistakes, adjudications, everything else. It's a much finer screen than RLAs by far.
I'm just asking, when you say, I don't know if you're using the paper in your risk limiting image audit. What is
that's the point here, is that we would do the first
verified
part, which is
images
the risk limiting image, the image part of it, and then essentially we'd be pulling, this just goes through a review, and then central to image audits, are the images valid? Okay, that's the question you're asking.
Yeah, thank you.
You need a way to verify that. And so then that's when we have a risk limiting ballot image audit, where we do the full ballot image audit plus review a paper.
Thank you, Ray. I missed this part of it.
No, we just, I didn't even mention this, but this is one thing that we've been working on, but I wanted to, because it always, because Paul was asking these questions, he hasn't seen this analysis that I did. I know some other people haven't either. And so I thought, okay, I'll just kind of go over this again to show you, like, here's where I'm coming from. I'm just trying to get the job done. Okay. I don't really have a position, except that I usually can't get to the paper, right? I mean, you say, well, let's go review paper. Getting to the paper is something I haven't been able to do.
I know, and
I've done
that's why I asked
lawsuits
the
trying to get to
question.
paper, and
Right.
it's not there. So
I know.
we got to get the images made so that they are more and more trusted, and that the opening for this potential hack is minimized. And then the ballot images will basically stop that. I think it's overblown to some extent, how easy that would be to be, because people in their minds say, and it's very valid, you know, look what smartphones can do. Basically, how big is that? That could be put into any voting machine, and it could definitely do it. We have a Cray computer in everybody's hand right now, what it used to be. So it could do it. Yeah. But the reality is, though, in those embedded systems, they're pretty simple, and you're not just going to be able to go in there and make a change like that without, it'd be very obvious.
I know, Ray. I just don't want to set up an argument.
No,
that
that's
then
why.
turned around against us, saying you didn't want this is what you wanted. We gave you what we wanted. Now we're not going to give you any more. So I'm always following up with that. Thank you. This is amazing. I got to go. And
Okay, thank you, Mimi. So what we can do is we can take individual precincts and get them scanned, and then AuditEngine now will take those precincts and compare them with the results as well. So we have a systematic way to do it. It doesn't mean you have to go in and look at every single ballot and compare it. You just get a batch, you run them through another scanner that's not the same one as the original. You have a whole bunch of scans of those batches. You can compare them as much as you want and see that they're the same. And then we take that and we compare that with the result. We do basically analysis of those same images and then look at the same result. I think people will, as they go through the ballot image audit, they'll see like how intense the checks are.